Hello everyone. So this is the third video on impact of jets, and after this we will be moving to the details of the turbine. So before that we will be discussing special cases of impact of jets in this session. So first we will look into a force exerted by jet of water on an unsymmetrical moving curved plate when the jet strikes tangentially at one of the tips. So all these cases can be visualized as the practical cases involving in the calculations related with turbines and all. So here the figure shows a jet of water striking a moving curved plate. This moving curved plate is also called as vane. So in the coming lectures we will be calling it more we'll be giving it the name vane. So here the jet of water is striking the vane tangentially at one of the tips, as you can see in this figure. As the jet strikes tangentially, the loss of energy due to impact of the jet will be zero. So because the vane is so designed like this, there will be no loss because it is hitting tangentially at one of the tips. So in this case, there is movement for the plate, and the velocity with which jet of water strikes is equal to the relative velocity, as we have seen in the last video. Also, the plate is also moving in different direction of the jet. So here, the plate or the vane is moving in different direction, and the jet is moving in another direction. So the relative velocity at inlet will be equal to the vector difference of the velocity of the jet and the velocity of the plate at the inlet. So in this session onwards, we will have to draw figures as you have seeing here in this slide. These figures are called velocity triangles. So the velocity triangle, this is a velocity triangle. This is the velocity triangle at the inlet, and this is the velocity triangle at the outlet. So in this video session, we'll be looking at how to draw these velocity triangles. So before that, let me introduce the terminologies associated here. So these are the terminologies. You can have a look at all these things. Some of it are already being discussed in the last session. So here VR1 is the relative velocity, and alpha is the angle of the direction of the jet and the direction of motion of the plate. It is known as guide blade angle, and you can see this angle alpha here. And there is another angle called vane angle at inlet, and it is here mentioned here, theta. So it is the angle made by relative velocity VR2 with the motion direction of motion at inlet. And there is VW1. W means world velocity. That is VW1 is world velocity at inlet, and VF1 is the flow velocity at inlet. So this VW and VF1 are the components of the relative velocity, or the components of V1. So as you can see here in this figure, this is V1, and this is V1, and the components of V1 are VW1 in the horizontal and VF1. So this makes a triangle ABD. And there is another, the relative velocity is drawn like this. So VW1, it is also known as the velocity of whirl at the inlet, as I have told earlier. Now similarly, all these terminologies are defined at the exit also. Here instead of angle alpha, here at exit we will have beta, and instead of theta we will have phi. So these triangles, that is triangle ABD and triangle EFG are called the velocity triangles at inlet and outlet respectively. Now we'll look into how to draw these velocity triangles for a given problem. Now first one, velocity triangle at inlet. So first we have to take any point A and draw a line AB which is of the magnitude V1, and direction, which means line AB makes angle alpha with that of AD. Next, draw line AC is equal to u1 in magnitude. Join C to B. Then CB represents the relative velocity at inlet. The loss of energy at inlet due to impact is 0. Then CB must be tangential to the vane at the inlet. Then drop a B perpendicular vertical line in the downward direction to meet the horizontal line AC at D. So here all these lines, BD represents VF1, AD represents VW1, and angle BCD means vane angle at inlet. You can refer the figure to better understand the steps. The steps are being clearly mentioned here. So you have to follow these steps in all the problems, and you have to draw the velocity triangles in problems which are demanding the diagrams to be drawn. Similarly, in similar fashion, you can draw the velocity triangle at outlet. So that is being explained here. And here also EH is the velocity of flow at outlet, and FH VW2. Okay. Now the conditions are, if the vane is smooth and having velocity in the direction of motion at inlet and outlet equal, then you will have u1 is equal to u2, which is equal to u, that is direction of the velocity of the vane in the direction of motion. And also we will have another condition, vr1 is equal to vr2. These two conditions you have to keep in mind. This will be useful in solving problems. Now again, mass of water striking the vane per second is rho A into vr1, that is the relative velocity at inlet, where A is the area of the jet, R is the relative velocity, and the force exerted is obviously mass into the initial velocity minus final velocity in the direction of motion of the jet. But initial velocity with which jet strikes is vr1. Therefore, the component of velocity in the direction is in the direction of motion. That is, in all these derivation, we are more interested in the direction of motion. So we have to take that component in the direction of motion. That is vr1 cos theta, which is equal to, from the figure we can see that vr1 cos theta is vw1 minus u1. You please refer the figure, then you will understand how this has come. Similarly, you will get the relative velocity component at the outlet, minus vr2 cos phi, minus, you can see minus because it is in the opposite direction, and from the figure again you will get the expression like this. And substituting all these values in your equation for force exerted, you will get the expression like this. And this, let us call it as equation number 3. Equation number 3 is true only when angle beta is an acute angle. Beta is equal to 90 degree, then these two lines coincide and VW2 becomes 0. Hopefully you should try to learn this with the figure, keeping the figure and seeing the figure. Then only you will understand how this expression, each of these expressions have come. So so if the beta is 90 degree, the expression changes to like this because VW2 becomes 0. And if beta is obtuse angle, just we will have a negative sign in this expression, and that is being written here. So as a general equation, we can write Fx is equal to rho a Vr1 into Vw1 plus or minus Vw2 as a general expression. And depending upon whether it is acute angle or obtuse angle or 90 degree, beta angle 90 degree, you can choose the appropriate expression. Now again, work done is being written here, which is force into the distance in the direction of motion. Again here the distance is the velocity is distance per second is velocity, and the velocity that we substitute here is the velocity of the vane, because work is done on the vane or on the plate. And work done per unit weight, you can express this in terms of unit weight, and you will get the expression like this. Again, you can express it in another in unit mass also. This is the expression for work done per second in unit mass. And finally, you have to find out the efficiency of the jet. Output remains the same, that is work done per second is the output, and input, as we have seen in the last few problems in last video session, it is the initial kinetic energy. which is equal to half mv1 square, and finally you get the expression of efficiency like this. Now we will look into some numerical problems uh, to better understand this portion. Water having a velocity 20 meter per second strikes a curved vane which is moving with velocity 10 meter per second. Jet makes an angle of 20 degree with the direction of motion of vane at inlet and leaves at an angle of 130 with the direction of motion of vane at outlet. Calculate the vane angles so that water enters and leaves without shock, and work done per unit weight of the water striking per second. So here is a problem in which velocity of the jet of water is given. So what all things are given. These things are given here. Jet makes an angle 20 degree with the direction of motion of vane at inlet. So it is the inlet angle. So we are denoting it by alpha. That is guide blade angle. And similarly, direction of motion with the leaves at an angle of 130 degree to the direction of motion of vane at outlet. So from this figure, you have to draw the velocity triangle here. Then you will better understand the water leaves at 130 degree. So this total angle is given 130 degree. From that angle beta can be easily find out 180 minus 130 degree. So beta is 50 degree. So you must be careful while indicating beta. Beta is not 130 degree. The direction of motion of vane is given here. So you have to subtract 180 minus 130 degree to get the beta angle. So here again in this problem there is no loss due to the shocks. Therefore u1 is equal to u2, which is equal to 10 meter per second. That is our velocity of the vane is 10 meter per second, and vr1 is equal to vr2. Therefore there is no loss. So you will have to draw the velocity triangles as shown in this figure. First draw v1, then vw1, then complete this figure. Then draw BC and mark all the angles. Similarly, in similar fashion, we have to draw the same. You have to follow the same steps and draw the velocity triangle at the outlet. Once the velocity triangle is given, is drawn, and all the terms are marked accordingly, it will be much easier to solve the problems. And you must take you must mark very clearly and with utmost carefulness. You should mark all the terms, that is v1, vr1, u1, vw1, angle alpha, beta, theta, etc. All this had to be marked very carefully because then only we can solve the problem correctly. Now the vane angle means the angle made by the relative velocity at inlet and outlet, that is theta and phi. So theta and phi are called vane angles, and alpha and beta are called guide blade angle. So these two terms you must keep in mind. As I have told earlier, you have to apply the concepts of trigonometry here and look at the triangles. For that only you have to draw these velocity triangles correctly. So in triangle BCD, refer to BCD. From that tan theta is equal to BD by CD. So BD can be VF1 and CD we can write AD minus AC. You can you can solve this problem by looking at this velocity triangle. So we are given the value of Vf1. Vf1 can be found out as Vf1. Again Vf1, to get Vf1, see the bigger triangle, that is ABD. So V1 sine alpha is Vf1. From the figure you can clearly see this. So V1 is given 20 and alpha is given sine 20. So you can find out Vf1. Similarly Vw1 is the horizontal component AD. So it is V1 cos alpha. Substituting the value, you will get the answer. U1 is 10 meter per second. So accordingly, you will get the answer of theta. Now once theta is obtained, again refer the triangle BCD in inlet side. This is inlet side. This is outlet side. So again sin theta is equal to Vf1 by Vr1, or to get the relative velocity Vr1, Vf1 by sin theta, you can get the Vr1. And but we have, because there is no stroke or no energy loss, Vr1 is equal to Vr2. Vr1 and Vr2 are the relative velocities. And again, applying sine rule, you can easily find out the value of phi here. You can see the steps. Now the second part of the problem is to find out the work done per unit weight per second. So we have an expression for that already. So here in this question, beta angle is 50 degree. So it is an acute angle. So we will put the work done, write the expression as 1 by g Vw1 plus Vw2. This plus sign because beta is an acute angle. So we have already got the values of all these. Substituting the values, we will get the answer of work done per second as 20.24 Newton meter per Newton. Now we will look into another problem. A jet of water having velocity 15 meter per second strikes a curved vane which is moving with velocity 5 meter per second in the same direction as that of the jet at inlet. The vane is so shaped that jet is deflected through 135 degree, and the diameter of the jet is 100 mm. Assuming vane to be smooth, find force exerted, power exerted, and the efficiency of the vane. So here again, first we will note the given things, and when we draw the velocity triangle, the velocity triangle will be like something like this. So you can see that here at inlet you have, it is not a triangle, rather it is a straight line. Why? Because here the guide blade angle is not given, that is the angle alpha is not given. So once you draw the all these velocities in this figure, you will get a straight line. First you will draw v1 and then u1, join cb, and mark all these things, but the alpha angle is not given, so we will take alpha angle to be 0 degree and then solve the problem. And one more thing to note here is that in the problem it is given that the inlet jet and vane are in the same direction, which means here indirectly they are telling that alpha is equal to 0 degree, and that is the reason why this inlet has become inlet velocity triangle is like a straight line. So again here phi is that is the vane angle at outlet is 180 minus 135, 45 degree, and we can then after drawing this velocity triangle we can solve the problem. So as the vane given is smooth, here again Vr1 is equal to Vr2, and from the inlet velocity triangle we can see that Vr1 is equal to Vw1 or V1, we both are equal, V1 minus U1, and you will get the answer like this. Outlet velocity triangle, again Vr2 is equal to Vr1 because there is no loss, and also U2 is equal to U1, which is equal to 5 meter per second. So Vr2 cos phi, you must refer to this outlet side, and finally you will get the value of Vw2, that is world velocity. W means world velocity at outlet is equal to 2.07 meter per second. Now once you have got Vw2, Vw1, we will solve force exerted, because force exerted, the expression involves Vw1 and Vw2, and again here beta is 45 degree, which is an acute angle, so we will have the plus sign here. Substituting the values, you will get the answer 1340.6 Newton. Again power is given by Fx into U, this much watts, or dividing it by 1000 you will get 6.70 kilowatts. And efficiency is output by input. Output is work done per second, which is again 6,703, and the kinetic energy is half mv square. So substituting the values, we will get 50.5% efficiency. Now coming to the next session, that is force exerted by jet of water on a series of vane. So this is the figure showing a series of vanes or plates which are attached to a wheel, and as you can see in this figure, a jet of water is striking the first vane, and then it is being rotated, and suddenly next vane comes in front of the jet of water, and this process continues. So this is a practical case. The earlier cases of a single moving plate, maybe flat or curved, was not a practical one. In fact, it was only a theoretical case. In actual practice, we find that, especially in the case of turbines, large number of plates are mounted on the circumference of a wheel, which are fixed distances apart. So when the jet of water strikes a plate, due to the force exerted on that plate, the wheel starts moving, and the second plate mounted on the wheel appears before the jet, which again exerts the force on the second plate, and the third plate comes into picture, and this process rotates, and each plate successively appears before the jet, and jet exerts the force on the plate, and thus the wheel starts moving in a constant speed. This is how the turbines are working. So these are the terminologies involved: V, D, A. So I'm not going to explain all this because you are already familiar with all these terms now. And the jet velocity, striking velocity is V minus U, where V is the velocity of the jet and U is the velocity of the wheel. And the force exerted, you will have expression like this, and work done will be force exerted into the velocity of the wheel. And here again, to find out the efficiency, you will have kinetic energy of the jet per second, half mv square. So substituting the value, you will have the final expression like 2u into v minus u by v square. So this expression is very important. Now, to find out the maximum efficiency, to find out we have the expression for the efficiency here, and what is the condition for getting the maximum efficiency. So whenever we go for maximum efficiency, we find out the we differentiate that with respect to a constant. So here the given jet velocity, the efficiency will be maximum when we have d eta by du is equal to 0. This is the condition for maximum efficiency. We all know the condition for maximum. So when we differentiate it with respect to u and equate it to 0, we finally get the expression as u is equal to v by 2. That is, or in other words, what does it mean? It means that the wheel velocity or the vane velocity must be a half of the jet velocity. That is the condition for maximum efficiency. I repeat, the velocity of the vane should be half of the velocity of the jet for the condition for this to be maximum. And substituting this value here, what is the maximum efficiency? We will get maximum efficiency to be 50%. So this is an important question in this part. So hope you have understood it. Now after this session, we will be solving problems related to turbine. So before that, you should have a thorough knowledge of the how each turbine is working, and what are the different types of turbine, and then we will look into solving problems related to each of the category of the turbines. So hope you have understood the session on impact of jets. In the coming lectures, we will be moving to the problems related to turbine.